In this lesson, we're going to talk about how we can take a set of data and create a linear function based on that data. Now, notice we're talking about multiple pieces of information, where in the 1.7 and 1.8, we were just given 2 points. And so here we're given multiple pieces of information. So we want the Desmos to use all this information to create a linear model. But we first have to decide whether there's a linear relationship with these points. And so we can't just take the first to the last, we have to look at all of those. So again, the definition of linear is that we have a that we have a rate of change that's constant through all the data points. And so if we recall, when we do a rate of change, we always have the change in output. So in this case, it's the change in P, the pollutants in parts per million, over the change in years, which is the change in time. And we have to do this for every data point. And so when we calculate this, we know that we're going to have some value, and then we know that our labeling is going to be parts per million, which is the output labeling per year. So this will equal whatever the value is there. And so what we have to do is we have to calculate the rate of change for every single one of these data points. So we want to go, and I'm just going to start from the top and go down. Remember, we're thinking about ending minus beginning, although we do not have to necessarily do it that way as long as we keep our ordered pairs correctly. So we want to do 5 minus 0. We want 9 minus 5. And again, the outputs would go on top, so that would be 4.7 minus 6. Then we have 3.9 minus 4.7. And so we do this for every single one of these. So now we have 10 minus 9. We also have 11 minus 10, 12 minus 11, 13 minus 12. So, and you'll fill in the outputs for each one of these and make that calculation. And we want to determine, are these values constant? In other words, they have the same answer rounded to 2 decimal places. So if you just round to 2 decimal places, you can kind of compare them. Or is it nearly constant? If it's nearly constant, pretty close, then that means that we can model this with a linear function. So go ahead and calculate those and determine whether that they're all the same or that they are close enough to being the same. Okay, as you saw from those calculations, your rate of change was near negative 0.26 parts per million per year. They all hovered around the 0.26 and 0.25 and somewhere right around there. So, and those rate of change were negative. Now, one thing about Desmos is we have 2 different types of table features in Desmos. So the table feature we had been using is if we already have a function. So if I have f of x equals negative 2 raised to the x, I could create a table. I would go to the gear, and then I would change it to a table, and it would create a table for me. Well, in this case, we don't have the function itself, we only have information. So we need to add a table. So we're going to go to the plus symbol, and we're going to add a table versus create a table. And Desmos always starts naming it x1, y1. And so we're going to go ahead and put in the input values in our X column and our output values in the Y column. Okay, with our data in Desmos, you'll notice that on the note sheet that you have this linear statement that says Y1, and then the approximate symbol, AX1 plus B. This is what the notation that Desmos uses to create a linear regression. Now notice that this is approximate and not an equal sign, because a regression model by definition is a best approximator of the given data, or best approximates the data. So that's why there's not an equal sign here. You'll also notice that this is written in slope-intercept form. Well, so this is just kind of telling you what Desmos is going to do. So we're going to look at our table here, and you'll see at the top left-hand corner where it says line 1, just below it, it says add regression. So we're going to click on the add regression, and you'll notice that there's actually a drop-down menu here, and we can do multiple different regressions. You'll do some of these in this course, and you'll do some of those also in your Math 151, your college algebra course. So click on linear regression, and we now have the linear regression model. We also have this information R squared and R. And this information is telling you how closely connected or how closely approximating this model is, this function is, to the data set. And so I'll talk briefly about that in just a minute. So we're going to go ahead and round to 2 decimal places our function. So we know that our function is P of t, and rounding to 2 decimal places, we have P of t equals negative 0.25t plus 5.99. And then we also have an R squared value equal to, I believe it was 90.9949 or 99.49%. So 99.49%. So this is saying that this model is 99.49% accurate to the data. So it's just off by a little bit. So now, interpret the meaning of the constant rate of change. So our constant rate of change notice that we're not looking at the data, we're not looking at our calculations that we've done before, we're simply looking at what we have written in for our function. And so the constant rate of change is negative 0.25 parts per million per year. So each year, the concentration of the concentration of carbon monoxide pollutants decreases by by 0. We don't need the negative there. 0.25. And again, if you want to put the ppm after that, you can, just so that sometimes it sounds better, but it doesn't matter whether you put it there or not. Now our vertical intercept, remember this is 0, comma, our vertical intercept value, which is right there. So we know that our vertical intercept is 0, comma, 5.99. Again, we're not looking at the data, we're only looking at the model that we just created, our function that we created. So we would say each year, or sorry, not each year, but in 1990, there were 5.99 parts per million of parts per million, I guess, CO pollutants. Now we need to find the horizontal intercept of the model, and this time we want to answer that to 1 decimal place. And so now if we go back to Desmos, because now we can see our function here, we can drag along till we find the horizontal intercept, and that horizontal intercept is 24.1. So we know we have 24.1 comma 0. That's our horizontal intercept. And so 24.1 years after 1990, the concentration level, or the CO2 or the CO level, was 0 parts per million. However, this is not practical because there will always be pollutants. Okay, so we have, again, everything is based off of the model that we have created, that Desmos has created, and the information, and really Desmos is using all of the different data point or decimal places here. So we can't really find this answer by hand unless we're using all of the decimal places. So it's best to use Desmos to find that answer.